Okay, we are moving on here. This is problem number 16. And I forgot to get the paper over here. Okay, there it is. A ball was thrown downward from the top of a building with an initial speed of 20 meters per second. It strikes the ground after 2 seconds. How high is the building, assuming negligible air resistance? Alright, so as always, I gotta draw it. So we're on a ball, or on a building, and we're throwing the ball, not dropping it, we're throwing it. So we're actually giving it an initial velocity down of 25 meters per second. And it strikes the ground, I know, 2 seconds later. And what do we want to know? We want to know how high is the building. Okay, so again, I'm going to draw the velocity time curve here. So I am, oh, I did it again. This is going down. Let's draw it up like this because I need a negative velocity. It's pointing down, so my velocity should be negative. So we're down here on the bottom side of this chart. So my velocity starts at 0. It's going negative 25 because it's pointing down. So I actually said that incorrectly. It's not starting at 0. It's starting at some negative value, negative 25. But it's a free fall, so it's accelerating down. So it's going to be like this. The velocity is, the magnitude is increasing, but it's still pointing downward, therefore it's still negative. The slope, of course, as always, is the acceleration, which we know because it's free fall, 9.8 meters per second squared. And we know it after some point in time it hits the ground, and that's 2 seconds. So what do we want to know? We want to know what is the distance that it travels in this 2 seconds time frame. So what am I looking for again? I'm looking for a formula that's going to relate what I know, acceleration, and do I know velocity? Well, I know the initial velocity, but I don't know the final velocity. I don't know what the final velocity is at this point, so that wouldn't really help me. But I do know distance, or I'm looking for distance, and I do know time, and I do know acceleration. So is there an equation that relates distance, time, and acceleration? And yes, you should be well practiced with it by now. It brings us to this equation right here. Well, not that one. That one's velocity and distance. We want distance, time, acceleration. So this is the equation we want. And again, I'm going to bring the initial x over here. So I'm going to call that delta x equals v initial delta t plus 1/2 acceleration delta t squared. Now it's important to point out this time that my initial velocity is not 0. So I don't cross it out. It doesn't go to 0. I need to keep that term in there. So what do I have? Initial velocity is 25 meters per second. What's the time frame I'm looking for? 2 seconds. Plus 1/2 acceleration, 9.8 meters per second squared, times delta t squared. Don't forget to square it. So that's 2 seconds squared. Okay, I don't need to do any unit conversions. They cancel nicely, and I'm left with meters and meters. So let's go ahead and plug that in and see what I get here. 50 plus 9.8. Helps if I turn it on. 50 plus 9.8 divided by 2 times 4, I could have done that in my head, equals 69.6 meters. Now looking up here at the answers, obviously it's looking like they're wanting me to round it to one significant digit. That's interesting. Why one significant digit? That has 2. That has 2. Well, they might be wanting 2 significant digits. If I were to obey the rules, 2 and 2, oh, time is only 1. Yep. So I need to round it to only one significant digit, which means this becomes 70 meters, and that gives me the answer D. Okay. Let's go ahead and also move on to problem number 17. Problem number 17 takes me to the next sheet. And we get another ball throwing problem. A ball is projected upward. Projected, that means it's thrown, not dropped. Projected upward at time t equals 0 seconds from a point on a flat roof 10 meters above the ground. The ball rises and then falls with insignificant air resistance, missing the roof, and strikes the ground. The initial velocity of the ball is 58.5. Consider all quantities as positive in the upward direction. At this time, the vertical velocity of the ball is closest to what? All right, a lot of info. Again, let's start by sketching it. So I'm going to draw my building. And they tell me it's 10 meters from the ground. So 10 meters from the ground, and I throw a ball up. It's going to come back down, miss the roof, and hit the ground down here. It rises and falls, misses roof, strikes. The initial velocity at this point right here is v equals 58.5 meters per second. What else do I know? Time, oh, okay, at a particular time they want me to find the velocity. Do I know anything else here? Well, I know velocity here equals 0. I know acceleration equals 9.8 meters per second because it's a free fall problem. So let's go ahead and draw our velocity time curve. Now what do I get here? I'm starting with an initial positive velocity. At some point the velocity goes to 0 and then it goes negative. So I have a curve that looks something like this. Completely missed my dots, but you get the point. 58.5. Do I know the time? Nope. I don't know how long it takes to go here, and I don't know how long it takes to go there. I do know the slope is 9.8 meters per second squared. And I also know that it covers 10 meters. Nope, I don't know that. I know actually, let's draw something here. I know when it gets to this point right here, the velocity is again minus 58.5 meters per second. Because it goes up and comes back down, it's going to have the same velocity at the same height, but it's just reversed in sign. So it's going to come back down, and at some point here, it'll be down here at a negative 58.5, but it's going to go a little bit past that to some velocity that I don't know, because it's gone an additional 10 meters. So this additional amount that it went here, I know is 10 meters. But again, I don't know any times. It's asking me at time 5.97 seconds, what's the velocity? Well, in order to know that, I kind of need to put some kind of time markings on here. So let's look at what I know and see what I can find. I know acceleration. I know a velocity, a couple of velocity points, and I know a distance point, right? So do I know an equation that relates acceleration, velocity, and distance? Okay, we've used that one a couple of times now, so we're right back to this one, right? So let's copy that equation down here. V final squared, v initial squared, plus 2 acceleration delta x. Okay. Now this one's got to be a little careful here, because in this case, if I'm going to use this distance, that means I'm looking from I'm going to apply this equation to this little spot in time right here, because I know the starting velocity. I don't know the final velocity though. Maybe I don't want to use that one. I want to use something that gives me time. I changed my mind. Let's not use that one. Let's use this one, because that relates time to distance and velocity. Let's use that one. That one will get me directly there. So let's try that one instead. Move the initial x over here, so I would have delta x equals v initial times delta t plus 1/2 acceleration delta t squared. Don't forget that squared. Okay, this one will get me more directly there. So I lost track of where I was going. All right. Be careful, the initial velocity is not 0 like we've done on some. If we're looking at this time frame, I know the initial velocity. I don't know the final velocity, but it doesn't matter. I don't need it in this equation. I know distance, I know initial velocity, and oh, that's not going to be very pretty. I think I changed my mind again, because that's not going to be fun solving for delta t. Let's see what the delta t is to get to this point right here. So let's go from this point to this point and see what that t is. So what's the delta x? Oh, I don't know that either. Okay, never mind. I'm going to go back to, no, I do want to use this one.